This video is meant for Mrs. Rose's AV Calculus class with slightly harder optimization problems. Alright, a rectangle has its two lower corners on the x-axis and its two upper corners on the curve 9 minus x squared. So that's a perfect parabola. And my y-intercept is at 0, 9, and my x-intercepts are at negative 3, 3. And we've got this rectangle inscribed where our two lower corners are on the x-axis and our two upper vertices are on the parabola. Alright, so for all such rectangles, so you could draw lots of things. They could look like that, they could be shorter and wider. So for any of these rectangles, the question is, what is the largest area that one of these rectangles could have? So we know that we're talking about a rectangle, and we also know that its height is y, which is equal to the equation that they gave us. And then we also know that the width of the rectangle is, well, half of its x, so the whole width is going to be 2x. So our area is going to be A equal to 2x times y, or 9 minus x squared. So you can do, now it's in one variable, you can A of x equals 18x minus 2x cubed. So to optimize, or get the largest area, we want to find the relative maximum. We want to take the derivative of A of x and set it equal to 0 and find the relative maximum. So A prime of x equals 18 minus 6x squared, set that equal to 0. 18 equals 6x squared. 3 equals x squared. So plus or minus the square root of 3 equals x. To find our relative maximum, we are going to use the domain, which goes from negative 3 to 3, and break it up at our two critical points. And then we can pick numbers on the intervals. And we're testing the derivative of area. And when you plug in a negative 2, this is going to be positive 4, so this is negative. Plug in 0, positive, plug in that, it's negative. So here we're going to have a relative minimum, and here we're going to have a relative max. So the area has a relative max at x equals the square root of 3. And then y would be 6, because we have 9 minus x squared, and when you square 3, you get 3, so it's 9 minus 3, which is 6. So we need to make sure it's an absolute max. We're going to do if x is 0 and if x is 3. So if x was 0, we'd get 9 minus 0 times 9 minus 0 squared, which is 0. And if we take and plug in a 3, we're still going to get 0. So the maximum area is 2 times the square root of 3 times 6, which is 12 square roots of 3. Okay. For our next example, we have a sheet of paper that is 11 by 8.5, just a normal sheet of regular paper, 11 by 8.5, and we want to make an open box by cutting squares of equal size out of each corner. So the idea is, if you cut along here and cut along here, that you'd have a smaller base, and then this flap would fold up, this flap, they'd all fold up and they form an open box. So if you cut the same cut and make squares so that your paper will make an actual box, then we want to figure out what is the largest possible volume, so we need a volume equation. The height is going to be the length of the cut because that's how high the box is going to fold up. The length, well, if we take the length of this paper, it was 11, but we made 2 cuts of length x, so it's going to be minus 2x, and then our width is the same idea, 8.5 minus 2x. So our volume equation in terms of x is x times 11 minus 2x times 8.5 minus 2x. Go ahead and multiply all of that out. Once you have your volume equation and you want to optimize it, we need to take the derivative and find the critical values by setting the derivative equal to 0 and solving for x. So we're going to do v prime of x equals 93.5 minus 78x plus 12x squared, and I'm going to rewrite it just to make it look more like what we're used to. And I mean, that decimal makes it really hard to factor, so what we're going to have to do to solve this is use the quadratic formula. So here goes. X equals negative b plus or minus square root b squared minus 4ac all over 2a. Alright, so we're going to do x equals 78 plus or minus, and then 78 squared is a big number. And then minus 4 times 12 times negative 70, or times positive 93.5, we get Now that we've solved the quadratic formula, we can reduce this to an actual decimal. Yes, I know, I don't like decimals, but let's go ahead and do it anyway. So now we need to do our relative max and mins, and we need to look at our domain. For a cut, we can either make no cut and go to 1.585, and then the next size cut we can make, it's not going to be this, because the paper's only 8.5 inches wide. So we need to do half of 8.5, which is 4.25. So this is too big of a cut. It's impossible to make that. So if you pick 1 and 2, and we're looking for the derivative of the velocity, if you plug in those numbers, you will get positive and negative. So we have a relative max at 1.585. So we can say that the volume of a box has a maximum when the height is 1.58. When you plug in 1.585 into the volume equation, you're going to get 66.148 inches cubed. Our third example, find the point on the graph of the function y equals x squared that is closest to the point 2 1/2. Alright, closest. We're talking about distance. The distance formula from geometry is the square root of x minus x1 squared plus y minus y1 squared. And what we need to do is plug in what we know into this equation. So x is our variable, and the point is at 2. Y is x squared, minus 1/2 squared. And we get that. What we need to do now is take the derivative, but before I do that, I'm going to square and like basically multiply this all out to make our derivative just a little bit easier. Going through all the algebra, you're going to get the distance equation equals the square root of x to the 4th minus 4x plus 17/4. Since you're looking for the smallest distance d, you really only need to look at the inside function, because if this is the smallest it can be, then the square root's the smallest it can be. So if we look at the function x to the 4th minus 4x plus 17/4, let's find the relative extrema of that. Okay, so, oh, I forgot the cubed.